I would like to start welcoming you all to the 24th webinar of the Interactive Center for Science and Technology in Amazonia, Brazil. I ask everyone to kindly leave the audio and the video streams turned off, except for the moment you're going to speak. Questions will be allowed after the webinar, unless otherwise requested by the speaker. The questions can be made using the chat. Today, we have the honor to listen to Professor William George Unruh, who is a Fellow of the Royal Society of London, Fellow of the Royal Society of Canada, and a foreign honorary member of the American Academy of Arts and Science. Among the distinctions awarded to Professor Unruh, I can mention the Rutherford Memorial Medal in Physics of the Royal Society of Canada, which he received in the year of 1982. Fortunately for us, Professor Bill Unruh has visited and given wonderful seminars at the Federal University of Pará in various occasions, including the years of 2004, 8, 11, 17, 19, and a webinar in 2020. Professor Bill Unruh is known worldwide for very important physical concepts and ideas introduced by him, some of them bearing his name, like the Unruh radiation, also known as the Unruh effect, as well as the Unruh vacuum. Professor Unruh is also responsible for the modern view of analog gravity by raising the question, experimental black hole evaporation, in the title of his famous 1981 PRL paper. At present, he is a professor of physics at the University of British Columbia in Canada, and a Hagler Fellow at the Hagler Institute for Advanced Research at the Institute for Quantum Science and Engineering at Texas A&M University, from where he will be speaking today. This time, Professor Bill Unruh will talk about a subject completely different from the ones I mentioned above, which is the falling slinky. And I should not make you wait longer to listen to him. Professor Bill Unruh, thank you once again very much for having accepted this additional invitation of yours. And from this moment on, the stage is yours.
Thank you very much. It's indeed an honor to be there. I wish I was in Brazil these days. All of my visits there, I've enjoyed it very, very much. And it's been a real shame that I haven't been able to visit in the last few years because of this disease running around the world. Anyway, I want to talk today a little bit about the slinky. I don't know how much I have to say, but we'll see that. The slinky was invented in the 1940s. A guy was trying to figure out how to support instruments so that the vibration and the rolling of the ship wouldn't upset the instruments, and built these big springs. And one day he had the spring sitting on his desk, and he happened to knock it off the desk, or actually sitting on some books is the story, knocked it off one of the books, and it sort of wandered down this pile of books that he had on his desk. And he went home to his wife and said, "Look, I think I've discovered something that might make a great toy." And he then spent a year or so trying to perfect it, and it became basically an instant success and has remained a success ever since. All it really is a spring. It's zero extension in the sense that each of the coils of the spring is very, very flat. As you can see here, I don't know, can you see my mouse cursor?
Yes, we can.
So if you look at these, you see that this is flat in the direction of the spring and is fairly wide in the other direction, making that as difficult, and I'm not sure how they do it. If you look at some of the stuff from the company webpage, they don't tell you either, because they're afraid that other people will learn how to do it and make cheap knockoffs. But there's a question that came up, and that's the following. What happens if you hold a slinky and you let it drop. Now, that's, I hope you all saw that. Let me look at this again, if I can figure out how, whoops. So what we have here, let's see if, whoops, nope. Nope. Oh, well, you notice that the spring is hanging, and it's hanging more widely spaced at the top than it is at the bottom, which is what you would expect. At the bottom of the spring only has to hold up a very short length of the spring, of the slinky, whereas at the top, it has to hold up a lot of it. And as we know, the amount of force exerted by a spring depends on how much you extend the spring. The more you extend it, the greater the force is. This is so-called Hooke's law, discovered around the time of Newton by Robert Hooke. And it became extremely important because it turned out to be an extremely good way of making clocks, because of the very great predictability of the force inside the spring. Anyway, he developed this toy and sold the toy for kids to play with, and they've played with it ever since. But what's going on here? If we look at this, let me do this again. You notice that the person lets go of the top of the spring, and notice what happens at the bottom of the spring. The bottom of the spring doesn't move until finally the top of the spring comes along and pushes it down out of the frame. Now, why in the world does it do that? The usual answer goes something like, when you release the top of the spring, the bottom of the spring is still supported by the stretch spring, so it doesn't move until the bottom finds out. Now, what in the world does finds out mean? It somehow discovers that somebody has let go of the top of the spring. And the usual answer is that there's a velocity of sound. In this case, sound is this compression wave in the spring. If you displace the spring, you get this compression wave that travels down the spring. That compression wave gets down to the bottom. And once that happens, then the bottom knows that it can start moving. Much of this is right, except the central idea isn't. It really doesn't have very much to do with the velocity of sound at all. And that's one of the things that I want to look at in this talk today. Oops. What do I want? So the first thing I've got to do is to do, as usual for physicists, is to do some mathematics. And I've got to define a few things. The first thing is, how do I label the slinky? Well, one could imagine labeling the slinky by just where is it located in space. This is called the Eulerian coordinates. You take a part of the slinky and you say, where is it? And that sort of gives you a label to where the slinky is. That turns out actually not to be very useful. Well, it is useful, but it's not the best way of labeling it. The best way of labeling it is what are called Lagrangian coordinates, where you basically label the slinky by the coil number. If you're right at the bottom of the slinky, you call that the coil number 0. You go up one turn of the slinky, that's going to be coil number 1. You go up 2 turns, that's coil number 2, until you get to the top, which I'm going to call coil number L for length. It's not a physical length, it's a length just in the number of coils that you need to get from the bottom to the top. There's another important thing, which is the distance. Obviously, this is a mechanical object, so the motion of that object in space is what we're always looking for when we're doing mechanics. And the vertical distance from the bottom of the spring to wherever you want to look at it, I'll call x. Not very imaginative. Physicists usually use something like x or z to label distances. The density of the spring in units of the coil number, i.e., it's basically the weight for one single coil of the spring, I'm going to call rho, which is just the mass of the spring divided by the number of coils, or m divided by L. K is the spring constant. How much does the spring pull back when you try and stretch it? And finally, there's a velocity, which I usually will call the velocity of sound. It's basically the velocity of these compression waves as they travel along the slinky. And it's the velocity in units of the coil number. In other words, if you start a little compression wave going, how long does it take that little compression wave to get up to a certain coil number? Not to a certain distance, but up to a certain coil number. That velocity turns out to be a constant. It's just equal to the ratio, the velocity of sound, or the velocity of the compression wave is the ratio of the spring constant divided by the density of the spring. Notice at the bottom, where the spring is not extended very much, the velocity of sound in real space is going to be very slow, because it goes a certain number of coil numbers per unit time. The coils are very close together, and so the actual physical distance that this compression wave will travel at the bottom of the slinky is going to be very slow, and it goes to zero as we get down to y equals 0, the bottom of the slinky. Now I'm going to use some concepts. I don't know whether or not you've heard them, whether or not you've looked at them. One is, and this is going to be using something called Lagrangian mechanics. The important things here are the potential energy of the stretched slinky, which is 1/2 times the spring constant times the rate of change of distance by coil number squared. That tells you how much energy you've put into stretching the spring. There's the kinetic energy, which is the rate of change at which these coils actually travel. It's the rate of change in time, how far x changes over a small amount of time t, times the density of the spring, which is just the, that's 1/2 mv squared, is just the kinetic energy. And you've got to sum over all of the coils, which we will write as an integral over all of the coils. dy, remember, is just the coil number, a small coil number. And then finally, there's the gravitational potential energy, which is the density times gravitation, 9.8 meters per second squared, times how high above the ground that particular point happens to be. This is the gravitational potential energy of any one of those single coils, or if you've got dy coils, then it's the potential energy of that little dy. To find out what the equations of motion of the slinky are, you write down this complicated expression, the kinetic energy minus the potential energy, the two kinds of potential energy, the stretch energy and the gravitational potential energy. You then take the derivative of that with respect to x, and that gives you these equations of motion. This one is wrong. There should be an x sitting in there. I can divide through this by, no, sorry. This is the equation of motion. Yeah. This is the equation of motion. I'm just going to divide through by G, by rho, and I get this equation of motion. It's a field equation. As with anything which has values at various points in space, you describe that in terms of fields, like electromagnetic fields, a temperature field, a sound wave field, and in this case, the position of the slinky field. And it's a second order differential equation, both in time and in space. It's a very simple one, which turns out to have a very simple solution. All right, what's going on? One of the very most important thing about finding this solution is to start off with your boundary conditions. And it turns out that for the slinky, there are two types of boundary conditions. One is the initial condition. That's a boundary in time at t equals 0. And at time t equals 0, the slinky is at rest. It's got 0 value of its time derivative of its velocity is equal to 0 everywhere along the slinky. Remember, the person holding it in the film was very carefully holding it so that the slinky would eventually come to rest everywhere. It's stretched, but it's at rest. The other boundary condition is that you cannot have any force due to the extended slinky at the ends of the slinky. The ends of the slinky are attached to nothing, and so if there were a force at the ends of the slinky, it would be trying to accelerate something with 0 mass, which would mean that it would immediately get infinite velocity. It would have an infinite acceleration and therefore immediately pick up infinite velocity. And as we noticed in the movie, that's not what happens. The ends of the slinky don't all of a sudden start moving at infinite velocity. F primed means just the derivative of f with respect to whatever the argument is of that function. F and h correspond to waves that travel in opposite directions along the slinky. Yeah. So as time goes along, the solution to the equation is f of y minus velocity times time and h of y plus the velocity times time. So you can always solve a one-dimensional wave equation in terms of these two oppositely directed waves. And that's all I'm doing here. We've got these two oppositely directed waves, f and h, and at time t equals 0, we want it to be at rest. So that this first equation here, written in terms of f and h, just give me this equation here. Then we have the endpoint boundary conditions, which just say that the stretch of the slinky at the end of the slinky had better be equal to 0, or else that slinky will be applying an infinite force. Sorry, will be applying a force to a 0 mass object that it's attached to, and you would have infinite accelerations, which don't work. Doing all that, we get this whole bunch of equations. We can solve all of those equations to find out what f and h are. And it turns out that f and h are exactly the same function. One of them represents the right-going wave and the other one represents the left-going wave. They're just equal to 1/2 of the initial stretch of the spring. And the initial stretch of the spring is g divided by the velocity of sound squared times the coil number that we've got in the spring squared. So as we noticed in that initial diagram, at the top of the slinky, these coils are widely separated, whereas at the bottom, you notice that the separation between the coils goes to 0. So one can solve all of these equations. I'm not going to go through the details. And what one finds is a very, very interesting behavior. So remember that we're assuming that this is all described by those equations, like sound waves going down the slinky. And what I have here is a graph of what the position is, x divided by L, as a function of y divided by L. Remember, this is the spring number. And initially, this curve here is the t equals 0 curve. It's just a parabola. So down at small y, values of y, the bottom of the spring, there's very, very little change in x as the coil number changes. As you get further up the spring, its space is wider and wider apart, as you expect. But as t evolves, what you find is there's this little kink develops, and that kink travels at the velocity of sound along this y direction. Remember, the velocity of sound is something that's in the y, is in the y coordinates. It has constant velocity of sound. In the x coordinates, it doesn't have a constant velocity of sound. However, notice that there's something strange here. So this is at a time 0.2. Time of 1 is the time it takes for the sound wave to travel from the top right back down to the bottom of the slinky spring. Notice up here, there are two separate values. For the same value of x, there are two separate values of y. That means that there are two parts of the slinky that are sitting in the same part, in the same location and space. Of course, that's impossible. In fact, as you go further along the spring, you find out that the spring has sort of reversed itself. What you find is that this top part of the spring, which is reversing itself, travels and falls at a uniform velocity. Now remember, this is in a gravitational field. So you usually expect things in a gravitational field to fall as, 1/2 gt squared. This isn't. The top of the spring falls with constant velocity. This distance from here to here is the same as this distance from here to here, etc. Furthermore, as the top part of the spring falls with uniform velocity, and the velocity, this kink, travels down the spring, down towards the end of the spring, what you notice is that the whole spring has reversed itself. This, remember, was the expanded part of the spring up here. This was the contracted. Now y equals 0 is the expanded part of the spring, and y equals L is the contracted part of the spring. If one were to let this go longer, you would then get the kink developing up here, and the spring would once again reverse itself with this part traveling at constant velocity. This part would keep traveling with constant velocity, and this part would travel with constant velocity, but twice this one. Then when the sound wave got to this end would travel at 3 times the initial velocity, etc. Now, you know that if the acceleration goes as g, then the velocity goes as v, as g times the time. So the velocity increases linearly with time, and it's happening here, but in steps. So first, the bottom of the slinky stays stationary, and the next part of the slinky falls always with a constant velocity. Then this part of the slinky falls with twice the velocity. Then this part of the slinky falls with 3 times the velocity, etc. Of course, we didn't see that in the movie. Why didn't we see that in the movie? Well, this whole graph means that you would have to have a transparent slinky. Namely, one coil of the slinky could travel through another coil. So up here, this part of the coil was above this point. And later on, this part of the coil is below that point. That, of course, doesn't happen in a real slinky. What happens instead is that as those two surfaces, those two coils come together, is they slam into each other. And in fact, if you look at a real slinky, they do this inelastically. They slam together and just stick together. So it's a completely inelastic collision between the coils, and the coils on top instead pile up. So this is just repeating what I've just said. We can watch what a real slinky does. And you notice the top all falls together, gloms together, and that just keeps falling down the slinky. Now you can't you can't see that. Well, to some extent you can see it. Remember that the spatial velocity of sound, measured in terms of actual distance, gets bigger and bigger as one gets to the bottom of the slinky. If one looked here, we notice that the velocity of the top, the velocity of the kink, if you will, seems to be almost constant, even though the slinky coils are getting closer and closer together. So this doesn't seem to be traveling at the velocity of sound at all. And in fact, what this is a shock wave. It's not a sound wave traveling down the slinky, but a shock wave. It's a discontinuity in pressure, in density, in velocity. The pressure in this case is the extension of the slinky. That's non-zero just below that junction and goes to zero just above the junction. The density obviously gets extremely high in that top part of the coil. And the velocity, there's a discontinuity in the velocity. And that's exactly how shock waves behave. And shock waves have another feature, basically all shock waves, namely shock waves travel faster than sound. You sort of usually get the feeling that, well, if you're traveling through a medium, nothing could go faster than sound. Well, maybe a jet plane could, but the air certainly can't go faster than sound. That's not true. Once you get a shock wave there, it can go significantly faster than sound. And that's what's happening in this slinky. As the top part of the slinky falls, it gathers the lower part. And this equation here is the equation of the rate of change of x position as a function of time. It's the velocity that we see in terms of distance as a function of time. And dy by dt is the rate of change of coil number as a function of time. Dy by dt, in fact, goes to infinity as we get down to the bottom of the slinky. Similarly, the rate of change of the mass just goes with the density times the rate of change of y as it gathers together the mass into that top slug. And one can write down the equation, Newton's equation, in terms of a momentum equation. Instead of F equals ma, you write it as F equals the rate of change of momentum. Here are the forces in this part. Here is the rate of change of momentum of the top caused by the bottom of the slinky. And one can find the solution, and I'm not going to go through the procedure. The general solution looks like this. Cubic equation on the left-hand side in terms of y, and on the right-hand side we get 1/2 gt squared. Well, we were able to divide out by g, so it doesn't enter into these equations. If c is not equal to 0, then if we look at y equals 0, the velocity of the slinky goes to infinity. Which is not, the physical velocity goes to infinity, which is not what happens. And we find that the rate of change, the velocity of the slinky, in fact, it itself does go to infinity. It's v, and this term here is all big. You can very easily see that this is always bigger than 1. So that, oh yes, it's a negative velocity. The thing is falling down. And so this is always bigger than minus v, i.e. it's the junction point is always traveling faster than the velocity of sound. So the velocity of the shock front is larger than the velocity of the sound in the slinky. So much larger, in fact, that as y goes to 0, as we get to the bottom of the slinky, the velocity in terms of y goes to infinity. That doesn't occur for most shock waves. It's very special for the slinky. Here's an example of a shock wave. This was the Alamogordo Trinity test. They made movies of that. This is 16 milliseconds after the detonation. The height of this bubble, is about 200 meters. This is 16 milliseconds after the detonation, which means that the velocity of this bubble has been on average 12 kilometers per second. Velocity of sound is 300 meters per second, not kilometers per second. So this surface wave, pushed by the intense heat and the explosion, the atomic bomb explosion, is now traveling at 36 times the velocity of sound instead of at the velocity of sound. At about this point, the explosion stops, the feeding of energy by the explosion stops, and you see another shock wave, purely an air shock wave coming out of it. As I say, this is not quite fair. In that short time, most of what's happening is that you've got the pushing of the successive explosion going on, which has been pushing the air out. If we wait a little while, if we look at the film a little bit further, we find that there's a shock wave in the air. Let's look at it here. Here's at about 80 milliseconds after the explosion, and we can see this little dark shadow in there coming off of this very, very bright explosion fed by all of the energy in the explosion. And this is just an ordinary air shock wave traveling at about twice the velocity of sound instead of 36 times the velocity of sound. At 90 milliseconds, it's traveled a fair amount more. At 109 milliseconds, it's traveled even further. There's an interesting story with this. One of the things that the people at that test site wanted to know was how much energy was released by this bomb. And they set up all kinds of instruments around it. And there was one guy there by the name of Fermi, Enrico Fermi, who's famous for Fermi problems. I'm sure that Luis has told you about Fermi problems, where you try and answer a seemingly impossible question just by using some absolutely elementary physics. What Fermi did was, before the bomb exploded, he tore up some newspaper into tiny little pieces. And then he counted down, he knew how far away he was from the bomb explosion. And it turned out that the velocity of sound from the bomb explosion was about 40 seconds. And then at about 36 seconds, he began to drop these tiny little shreds of newspaper from above his head down towards the ground. There was almost no wind at the time. So these things basically just dropped straight down until the shock wave hit. Then for a brief period of time, they were all displaced by about 2.5 meters. So during that fall from the top, from about 2 meters above his high down to the ground, the intense velocity motion of the air in that shock wave had pushed all of these tiny pieces of paper away by about 2.5 meters. Using that bit of information and knowing about shocks, he could calculate how much energy there was in those shocks. And it was about half the total energy of the bomb, about 10, the equivalent of the energy in about 10 kilotons of TNT. So the initial shocks, the air shocks, as you saw here, they were traveling about twice the velocity of sound. But the shock, of course, gets weaker and weaker as it travels away from its source, falls off as 1 over r squared, and very rapidly the shock wave is traveling at almost exactly the same as the velocity of sound. But he was still able to calculate how much energy there was in that. We can look at this shock wave in the slinky. We can look at dy by dt divided by the velocity of sound. Velocity of sound, remember, is a constant in y coordinates. It travels at a certain number of coils per second. But the velocity of the shock wave diverges, either in y. As we get near y equals 0, it's now up to 4. And for the idealized slinky that I've been calculating, where the width of each of the coils goes to 0, the velocity of the shock wave goes to infinity. The shock wave is, of course, being pushed by this heavy lump of metal, which is the congealed coils from the top of the slinky. They're being pulled down by gravity, and they're pushing those coils below them, and is what's making that shock wave and causing the shock wave to travel faster and faster in terms of the number of coils of the slinky. If one looks at the actual velocity, however, of that top lump, one finds that it's roughly constant from the top, where it goes at roughly the velocity of sound, to the bottom, it's traveling at about 0.6 of the velocity of sound. But remember, the velocity of sound here is the velocity of sound in y coordinates, not in x coordinates. The actual velocity of sound in the slinky in x coordinates goes to 0. So this is traveling much, much faster than sound would travel along that slinky if one had a movie of a little sound wave traveling along it. If one looks at it as a function of time, one finds that it still diverges, but not quite as rapidly. One can also look at the energy. There's the kinetic energy of the top of the slinky, the gravitational potential energy of the top of the slinky, the gravitational potential energy at the bottom of the slinky, which, remember, is not moving and therefore has no kinetic energy, and the potential energy of the stretch of the spring, which completely disappears by the time the shock wave gets to the bottom of the slinky. So what happens is that this stretch energy inside the spring basically gets converted into heat. The slinky is very different from shock waves in air, for example, because it's the heating of the air behind the shock wave that is driving the shock wave to travel faster than the velocity of sound. In this case, it's the mass behind in that top lump that's driving the shock wave to travel faster than the velocity of sound. It's not the heat. The change in temperature of the slinky as you drop it is much less than a degree centigrade. If you look at the total energy as a function of either of y or of time, you notice that the total energy starts up here and drops down as the slinky coils crash into each other, they convert some of the energy in the slinky into heat. But not all of it gets converted. Only about half of the energy in the slinky gets converted into heat. And the rest is now in kinetic energy of this big lump that's falling as you get down to the bottom of the slinky. So the slinky is this deceptively simple classical toy. It's a lot of fun to play with. If you can get a hold of one, do. It's fun to play with. It's fun to watch it walk downstairs, etc. But it also has an awful lot of rather deep physics in it. It's not simply the simple toy that one might initially think that it was, and can lead you into areas of physics which are basically fascinating. The velocity of sound, of course, is something that people have worked on ever since Newton. Shock waves, on the other hand, is something that really only started in this century, the detailed examination of how shock waves behave. And here you've got a very, very simple system where you can illustrate at least some of the features of how shock waves behave in this simple system. And I've just run out of slides and out of talk. So I think at this point I'll quit and open things up for questions. I apologize that I couldn't give this talk in Portuguese, but if I tried that, it would be completely incomprehensible.
Well, first of all, before we proceed, let me ask everybody to turn on their microphones for a huge round of applause to Professor Bill Unruh for his wonderful talk. Okay, so people that want to make questions, please either write down in the chat that you want to make questions, or either you just turn on your microphones after I give some panorama to Professor Unruh of the audience that he has had through his talk. So we had around 50 very selected people from all around Brazil. So representative from all regions of Brazil. So from North region, we have people from Pará. From Northeast, we have people from Paraíba, for instance. From Center-West region, we have people from Goiás. From Southeast region, we have people from Espírito Santo, Minas Gerais, Rio de Janeiro, São Paulo, all states. And from extreme south, we have people from Rio Grande do Sul. So obviously, we have the seminar is being organized by our university. So we have undergraduate students, graduate students, postdocs, teachers, professors, and technicians from our Pará University, like Igor Coimbra, Jorge Cassineiras, Jaime Urban. Not only people from Belém, but also from the cities of Ananindeua, Castanhal, Santarém, like Damião Meira Filho, that is participating from Santarém. We have people from all, different universities all around Brazil, like Felipe Rosa from Rio de Janeiro, George Unruh from Juiz de Fora, Minas Gerais, Humberto Belis from Vitória, Espírito Santo, Kepler Oliveira from Rio Grande do Sul, Lucas Celleri from Goiás, Marc Casals from CVPF, Nivaldo Lemos from Niterói, Federal Fluminense University, Odílio Aguiar from National Institute for Space Research, and Satish Kumar, PH from Unirio in Rio de Janeiro. So lots of people from all around. Thank you very much for participating. And I would like to know if you have questions. Otherwise, I have some questions. So from the chat. So Bill, there are lots of questions that I'd like to ask you, but obviously I have the opportunity to make it I have other chances to make it. So let me make, for me, which is the most important question. So I had
So there's some hands somewhere in there.
Yeah, I think Satish raised the hand to ask the question. So, Satish, I will be polite enough to pass the word to you. Make your questions first, and then I do my question afterwards.
Absolutely, no problem. Please go ahead. Yeah.
Please go ahead.
No. Please. You can go ahead. I can ask at the end. Yes.
Okay. So, Bill, well, I have had the pleasure to meet you for more than 15 years now. And what has impressed me from the beginning is that not only you have inspired me in my main field of research, which is gravity and quantum field theory in curved spacetimes, but together with us in this room is my Cuban friend, Jorge Castiñeras, that I think met you also in the first time you came to Belém. And by that time, I think we learned about that negative damping and the Tacoma Bridge problem that you have tackled, right, in the past. And when we were, I think, in Mosquito Beach, and I think we were, I don't know if you remember that, but we were watching that bar just vibrating with the wind by the river shore. And what has impressed me is that although you have very much oriented your mind to research, to take care of very, very deep theoretical physical problems, but also you have dedicated a part of your time to problems that come from real life, right? I mean, like this slinky that I just realized this year that you have been concerned with, but the Tacoma Bridge thing. And also, I mean, you told about the course in hydrodynamics, or I mean, that you gave. So I would like you to tell us about how you see, I mean, the importance that you think that people, in particular physicists or students, that they should give to these problems in real life. I mean, to make, like, I don't know if it's possible, but to make a parallel between very deep frontier physics and also this daily life physics, the physics of the problems that we face during our lives. Could you say something about that?
Sure. Well, I mean, from my point of view, physics is trying to understand the world we live in. And the world we live in is incredibly rich and has so many things that one can try and wonder about. And, you know, sometimes the answer turns out to be relatively straightforward. Very often you get into one of these questions and it turns out to be far deeper than you ever expected it to be when you first started looking at it. And, you know, ever since I've been young, I've just been curious about stuff and want to know and want to understand what's going on there. And, you know, the amazing thing is, as a physicist, I've been able to, you know, make a living, etc., trying to understand the world. And it can be in all kinds of areas, like the slinky. I can't even remember how I got into that. I guess somebody asked the question about what happens when you let go of a slinky. And I decided to try and understand it in some more depth than the sort of glib answer that one usually gets in the first year demonstration where this thing is demonstrated to you. Tacoma Narrows Bridge was the first time I saw that movie, which I'm sure you've all seen, of this bridge all of a sudden going into this massive oscillation. What's driving that oscillation? Why is that? Why in the world did that bridge suddenly go into this insane oscillation? I mean, it flops back and forth by 45 degrees until finally it broke apart and fell into the river. What drove that? There's obviously some feedback going on there. Physics of music came into this, you know, trying to understand how instruments work, and this whole sort of nonlinear feedback, self-limiting nonlinear feedback that goes on in virtually any continuous sounding instrument that one has. What drives it? How does the violin behave like a clarinet, which behaves like a tuba or whatever? What's the similarity between them and what's the difference between them? I just find that kind of thing fascinating. And in the physics that I've done, the sort of, if you will, serious physics that I've done, is trying to look at those kinds of similarities between various things that has really driven me in my curiosity and in trying to answer the questions, you know, how is a violin like a slinky, or how is a violin like a like the Tacoma Narrows Bridge? What's the similarities between them? What are the differences between them? It's a lot of fun, and I've been incredibly lucky that I've been able to spend my life and actually have people being willing to pay me for having as much fun as I do.
Okay, well, thank you very much. Let me then ask Satish. Satish, do you want to speak?
Yes. Is my microphone working? Can you hear me?
I can hear you.
Oh, okay. Thank you very much, because I had some problem. Thank you, Professor Unruh, for the talk. Like Louis mentioned, right? So we think of only serious physics, like black hole physics is important than thinking about slinky. But when it comes from you, it makes us feel happy. I'm very much interested. I don't like to distinguish between, like, black hole is more serious than slinky. I think they are the same. I think in the spirit of Feynman, I think everybody knows the story of throwing the plate and Feynman trying to calculate, and Hans Bethe saying, that's not, concentrate on quantum field theory. But Feynman is Feynman because he studied that kind of silly things. so only Bill Unruh can study this kind of things and make them cool.
No, any of you can do that. I mean, if you spend too much of your time on that, then the people that are paying you might start getting unhappy. But
so somewhere we have to strike the balance between surviving and doing cool things.
right, but you know, you don't want to be sitting there thinking about quantum field theory all of the time. Sometimes you just need to rest and think about something else. And you know, in those times you can sit down and think about this. It's like, you know, John Bell as well, you know, Bell's theorem. John Bell was hired by CERN as a accelerator designer.
Mm-hmm.
And he took his job very seriously, and simply, you know, when he was working at CERN, felt that that's what he was supposed to spend his time on. Then he went to Stanford for a sabbatical and felt he had a little bit more room there to think about other things, and discovered Bell's theorem, which is, of course, made him vastly more famous and brought much more attention to CERN than almost anything else that CERN did. So, you know, always keep your curiosity about the world going, because that's the only way, that you will stay sane. And I think it's also the only way in which you will really begin to get insights into physics.
Thank you so much for the comment. I have plenty of questions, but there are so many people to write. So in the equations that you mentioned, the density you wrote, it looks like the linear density. Is that correct? It's the mass per unit length.
It's the mass per unit coil. So
okay.
The density is how much mass is there in each single coil. So that the total mass is just equal to that rho
number of
density
coils
times the number of coils that you're looking at.
Got it. One last question. So what if we throw the slinky up in the air? Is it just going to go like a coil up and coil down? Nothing cool happens?
If you do what?
Throw the slinky up, vertically up. Or just drop it down without stretching it. Just drop it, the whole thing.
Right. I mean, if you just take the whole thing and drop it, then again, then nothing will happen. It's equal. It's in its equilibrium position. There's some interesting questions that are still open. For example, if you buy one of these slinkies, you can go ahead and grab the ends of it and pull it apart by about 30 meters, and that then the steel that's beyond the yield strength or the elasticity strength of the steel, and it will then have a permanent spacing between the coils. How does that behave if you hold it up and let it drop? Do you get these shock waves, or what you tend to get happening is little mini shocks forming and then disappearing? As the slinky, the equilibrium position of the slinky coils are not being right on top of each other, but are rather spaced away from each other. How can you analyze that kind of a situation? It's a much messier system than the real slinky, where the equilibrium position has each coil right on top of its neighbor. So that's sort of an open question that you can think about.
Or throwing the slinky from the airplane, just like the chain thing, right? So throw the slinky from the airplane, you'll be busy for the rest of your life. Thank you so much.
You're welcome.
Thank you, Satish. So the next question comes from Felipe Rosa. Felipe, please.
Hello there. Can you hear me okay?
Yep.
Well, I would like first to thank you for the talk. It was great as usual. And I think everyone here just loves this Slinky. I mean, it's a wonderful toy. But I must confess that I got really interested in your first system, the system that described what would happen if this Slinky were transparent, right? So have you thought about it in a way to realize physically this system? I mean, I just hear out of the top of my head, I just thought about like two asymmetrical rings, one small and one big, that you could glue with a very stretchable material, some stretchable tissue. Then you could, like, one could pass through the other and maybe realize that system. But have you thought about something more sophisticated or more physically doable?
I haven't gotten much more sophisticated than that myself. I mean, one of the possibilities is to make a spiral. So, have a piece of wire which gradually spirals in. Now the inside coils can go through the outside coil and go back and forth like this. The problem with that is, of course, that both the spring constant as you get into the inside coils and the density as you get into the inside coils, because they're much smaller, changes. So this is not a uniform slinky. It's a slinky which has a density and a spring constant. Now you could presumably, by choosing the right kind of wire, and right a graduated thickness of the wire, create one in which the spring constant and the density were just the same as in a regular slinky. I'm not sure. You could make it thicker, the inner one thicker, for example, to
try to compensate. Try to make one thing compensate the other.
Right.
All right.
In which one could do that? It would be neat to see, because it would be, that motion I find fascinating, that this sort of slinky keeps turning itself inside out.
It is. It would be amazing to see it happen. I mean,
each part of it keeps falling at constant velocity, and then it trades places, and then that part falls faster, and then you get the velocity going as GT, but in steps instead of continuously. So it'd be fascinating to be able to build something like that. I just haven't thought about it deeply enough to figure out how to do that.
Okay, yeah, that would be amazing. I'll try to get some smart people in my institute to think about that as well. Okay. Thanks a lot.
Well, thank you, Felipe, for a question. Thank you, Bill, for your answer. So the next question comes from Lucas Celery. So please, Lucas, you're speaking from Goiânia, right? It's good if you tell where are you speaking from. Please go ahead.
Oh, yeah. No, now I'm actually, I work in Goiânia, I'm based in Goiânia, but now I'm actually in São Paulo state. The university is basically closed, so I have nothing to do there. I'm not at ciência. Can you hear me?
Yes,
Yes, please, go ahead.
Okay. Thank you very much. Professor, thank you very much for the talk. It's really, really amazing. I mean, I never thought about these things. And when I start thinking about simple systems, is really good. My question is actually really
complicated.
Yeah, exactly. My question is really very naive. What happens if this link was a quantum fluid? It means a shock wave in a quantum fluid, like I don't know, Bose-Einstein condensate.
Right. Yeah, I haven't thought about that very much at all. It is certainly an interesting question as to whether or not you could get shock waves in that situation. One of the places where I know it's become an interesting question in the last while is it's again a classical system, but is in a purely gravitational system. Do Einstein's equations allow shock waves? Can you develop shock waves in a system that just obeys Einstein's equation, in the metric which obeys Einstein's equation? Can you get shock waves? And I've heard at least rumors recently, over the last 5 years or so, that people have actually discovered that you can get shock waves in systems like that, which is pretty amazing if it's true. So I think as soon as you start getting nonlinearities, the possibility of shock waves becomes realizable.
Oh, I see, but yeah, but this would actually requires the dynamics of the metric to change it. So it would not be possible to do this in an analog system like a Bose-Einstein condensate or things like this, because the system, I mean, they simply don't have Einstein's equation there.
I mean, there it's the Einstein equations themselves that are developing shock waves.
Yeah.
Whereas in analog systems, you always just sort of impose a background metric.
Exactly.
It doesn't obey Einstein's equations in any sense. But most of those equations are nonlinear equations as well.
Yeah.
And so you might expect to actually get shock waves in those kinds of systems as well.
Yeah, because I was just thinking, what would be a quantum shock wave? I have no idea.
Yeah,
I never thought about this.
I don't know how. I mean, the problem is that shock waves, as I said, are really a 20th century phenomenon, where people really started worrying about them and thinking about them and developing the theory of shock waves. And what that tells us is that even simple equations like the fluid dynamics equations, which you can write down in 2 sentences on a piece of paper, turn out to have these horrendously complicated behaviors. And if you start adding quantum mechanics to that, where everything becomes an operator rather than just sort of ordinary functions, even trying to understand what you would mean by a shock wave with these quantum operators becomes difficult to imagine. So, a shock wave in a quantum fluid sounds fascinating. I would shudder in a bit of horror at thinking about trying to actually analyze it, however.
Okay, thank you very much for the talk and for the answer.
That's why one has young physicists around, people like you guys, who aren't as afraid as us old guys of the impossibility of some of these problems.
Okay, thank you very much, Professor.
Okay, thank you, Lucas, for a question. Thank you, Professor Bill, for your answer. So we have one more question. It comes from, if somebody knows how to spell better, please let me know. It's Grigors Hashval. So he asked me to read. he asked me to read it because his microphone is not working. So he says, in your description, you used the Lagrangian action of a two-dimensional, one time, one space dimension x field theory. Later, you said that there is heat produced due to the inelastic collisions of coils. How would you include this in the original Lagrangian? Do you need to add some dissipative terms there?
Well, the answer is I cheated. So the equations of motion that I wrote down, I basically treated them discontinuously. Namely, that if the two coils are touching each other, then they stay glued together. I don't have any equation that says that that's what they're going to do, but I'm just making that assumption. And it seems to be a fairly good assumption for these coils of the slinky. But the whole treatment of dissipation in quantum systems is of real interest. Ralph Schutzhold in Germany, a student of his, Lange, and I have been looking at a model in which we try to look at a quantum field which has dissipation in it. And that dissipation is caused by another field which is coupled to this one, which can carry away energy from the first quantum field and causes it to damp out. And one of the reasons we're interested in that is to ask the question, if one has dissipation, for example, in the formation of a black hole, let's say even in quantum gravity, if there's some sort of dissipation that goes on there, what kind of a difference does that make to black hole thermodynamics, to the temperature that this black hole will produce as it forms? Does the dissipation, a la the fluctuation dissipation theorem, does that get changed by the presence of a dissipated field? We still don't have an answer to that. And, so it's a question of real current theoretical interest. And it's obviously of practical interest because every material that we have, that we know of, has some dissipation in it. And how can we get a good handle on that, and what kind of an effect does that have in a quantum system is a very interesting question.
Okay.
Simply adding dissipative terms in a Lagrangian doesn't really work, because Lagrangians tend to conserve things like energy. They don't dissipate energy. So what you need is you have to introduce something like an extra field, which is going to soak up that energy and conduct it away, take it away from the system. You can do that. You can make some very simple models like that without too much difficulty, but then solving them becomes more difficult.
Okay. So Grigor is acknowledging for your answer. And we have also other comments like Daniel Martinez, Professor Unruh, thank you very much for your amazing talk. And many people, I'm sure, that are amazed by this very nice talk by apparently simple experiment, but has lots of physics inside. Let me, just before we end, register that we had also people from Maranhão State that had registered their presence here. We have people attending from United States of America, apart from you that were speaking. We had Professor Newton Barbosa from Alabama, and we also have people from Portugal. Haroldo Lima Jr. is attending from Aveiro. So you had an international participation, also people attending from.
Wonderful. I hope they had fun.
Yeah, sure we had. So before we end, let me ask everybody to turn on their microphones once again for a final round of applause in retribution for this wonderful moments that we spent together, thanks to Professor Bill Unruh. Thank you very much, Professor.
Thank you.